Observations and Model Results Mean More Together, Updates on Phytoplankton Dynamics in the Salish Sea by Elise Olson, Susan Allen, Teresa Yarnikova, and Doug Latranell. Salish Model Ecosystem Lower Trophic, or SMELT, is an NPZD-type biological model coupled to a 3D physical simulation based on NEMO. The model domain is the Salish Sea on the west coast of Canada. The physical model has vertical resolution ranging from 1 meter at the surface to 27 meters at depth. Horizontal resolution is approximately 500 meters. The biological model includes 3 nutrients, 3 primary producers including the Mixotroph Mesodymium rubrum, 2 zooplankton groups, and 3 detrital pools. I'm going to describe 3 examples of cases in which the model and observations together provided more information than either could alone. First, we used the model results to analyze the contribution of nutrient injection by the Discovery Passage tidal jet to primary production in the northern Strait of Georgia. The video shows surface nitrate on the left, horizontal nitrate flux in the center, and vertical nitrate flux due to mixing on the right. The bottom panel contains a timeline with sea surface height at Campbell River near Discovery Passage. Nitrate is mixed to the surface in Discovery Passage and pulses southward with the tidal cycle, with the strength and extent of the surface nitrate plume modulated by both tidal amplitude and wind conditions. The model output allows us to examine in detail a process that is poorly resolved by observations at repeat sampling stations, shown in the upper left, which are typically sampled several times per year. Comparisons between the model and available observations, shown on the lower left, give us confidence in the model's ability to represent real-world conditions. We then interpret the model output and even perform experiments such as the one illustrated on the right, in which we rerun the model with Discovery Passage closed. This experimental simulation had 22% less depth-integrated primary productivity and 35% less depth-integrated new primary productivity than the base run over the region pictured, highlighting the significance of the Discovery Passage jet as a nitrate source in the northern Strait of Georgia. In the second example, we recognize that the model was missing a locally important process, the attenuation of light by suspended sediment in the Fraser River plume. An existing Environment Canada water quality buoy provided an excellent opportunity to force the river-suspended sediment concentration with real-time data. However, we needed additional data to constrain the relationships between turbidity and fine suspended sediment and between fine suspended sediment and light attenuation. Measurements we collected, combined with existing data, allowed us to implement a single size class suspended sediment model along with an improved parameterization of light attenuation. These developments improved the model's ability to represent chlorophyll concentrations in the plume region. The panels on the left illustrate the mismatch between the model and observations provided by Ocean Networks Canada along a ferry route connecting the mainland with Vancouver Island. Root mean square error is shown on the left and bias on the right, with the original model on top and the improved version below. With the new light attenuation model, both the root mean square error and the bias were reduced in the plume region. The table on the right describes the improvement in terms of the Wilmot skill score. The improvement was most significant during the spring freshet. In this way, after model data comparisons highlighted a weakness of the model, observations were used to constrain a new parameterization for light attenuation, improving the model's performance. In the last example, we interpret model results and observations together to better understand differences in bloom timing and phytoplankton abundance in different parts of the model domain. Generally, Juan de Fuca Strait is thought of as having a low standing stock of phytoplankton due to greater depth of mixing and associated light limitation in comparison to the more stratified Strait of Georgia with its strong Fraser River influence. However, our model results showed significant phytoplankton concentrations in Juan de Fuca Strait on levels similar to the Strait of Georgia in the summertime. The first 2 panels show mean chlorophyll concentration in the upper 10 meters versus year day for several years of model simulation. Time series from 2 points in the Strait of Georgia are presented in the first plot and from Juan de Fuca Strait in the second plot. Although we were initially surprised by the amount of modeled chlorophyll in Juan de Fuca Strait, model data comparisons showed similar biases in the 2 regions. The lower plots show the difference between modeled and observed chlorophyll versus year day, with Juan de Fuca Strait and the Strait of Georgia regions defined through a cluster analysis carried out by Teresa Yarnikova. Plotting the model data comparisons by year day sheds light on a plausible explanation for the difference between our expectations and the model results. Springtime sampling is often carried out around the time of the Strait of Georgia spring bloom, which precedes the model bloom in Juan de Fuca Strait in each year. Additionally, sampling in Juan de Fuca Strait is particularly sparse in summertime when the modeled chlorophyll there is high. Thus, a sampling bias may have skewed our expectations of Juan de Fuca Strait chlorophyll levels. In contrast, the model provides a continuous picture in space and time. A regional analysis of model phytoplankton, including the differing vertical distributions between Juan de Fuca Strait and the Strait of Georgia, can be found in the preprint of Teresa Yarnikova's paper currently in review at Ocean Science Discussions. We have provided 3 examples of ways in which model and observations together are more useful than either alone. An evaluated model was used to observe a phenomenon poorly resolved in available observations. New observations were collected and used to refine the model to address missing dynamics. And careful interpretation of seasonal and spatial patterns in model results and their comparison to observations led to a new understanding of regional bloom patterns in the Strait of Georgia and Juan de Fuca Strait. This work was made possible through funding by MEOPAR, which was supplemented by additional funding from MITACS and the Pacific Salmon Foundation. We are pleased that this modeling effort has had impacts beyond the creation of the model itself. For instance, in the course of model development, we identified a bug which was fed back to the Nemo Pisces developers. Our simulations have formed a basis for several other research projects, including extension of the model to include carbonate chemistry by Teresa Yarnikova, and an analysis of wind-driven upwelling and surface nitrate delivery by Ben Moore-Maley, both of which have led to publications. Ongoing work includes in-depth evaluation of model zooplankton fields and analysis of grazing rates by Karen Suchi, and coupling the system into an Atlantis ecosystem model for higher trophic levels by Rachel Lovendier. Outside of Susan's research group, a University of Victoria graduate student used model output to interpret findings of a survey of oyster farmers' impressions of changing environmental conditions, and graduate students at UBC have used the model results to provide spatial context for a one-dimensional oxygen-based primary production analysis. We are grateful to MEOPAR for providing the means to develop a modeling tool with broad applicability and relevance.